Hello and welcome to another video. In this video, we are going to be talking about continuity, in particular the continuity of different types of functions. So without further ado, let's get into it. Continuity. What is it? How can a function be continuous? Well, for a function to be continuous, you need to draw it from left to right without picking up your pencil. So this means no breaks and no jumps. All right. If there are breaks or jumps, then the function is said to be discontinuous. Rather than consider where it is continuous, it is much easier to consider where we might have discontinuities. Okay. So again, for a function to be continuous, that means that we can draw it without lifting our pencils. So that means no holes, no asymptotes, no jumps, none of that. All right. If there are any breaks, any holes, any asymptotes, or any jumps, then the function is said to be discontinuous. So with this knowledge in mind, let's take a look at a couple of examples here. So let's state whether each of these functions is continuous or not, justifying our answer. So the first one, here we have a polynomial function, right? X plus 2 squared times x minus 1 times x minus 4. And we can see here that this is going to be a polynomial of degree 4. And immediately we should be able to tell that this function is in fact continuous, right? I am able to trace it without ever lifting my pen or my pencil. That turned out a bit crooked, but you get the point, right? And so, yes, this function is continuous, right? We are able to trace it without lifting our pencils. Okay. So again, we have no holes, no jumps, no asymptotes. So yes, it is continuous. Okay, so polynomial function, continuous. Now, what if we have something like this? All right, so this function seems to be continuous. However, if I try to trace it, I'm going to come across that little area there that is a discontinuity. And a discontinuity such as this one is called a hole. So a hole means that the function is discontinuous. Okay, so if I ever have a hole, if I ever see a hole in a function, that means that the function is discontinuous. Okay? In other words, not continuous. All right. Now, what if I have something like this, like a piecewise function, right? Well, immediately we are able to tell that there is no way in which we can draw that without lifting our pencils, right? As a matter of fact, I can trace this line going from left to right, but then to go into this parabola looking portion of the graph, then I definitely do have to lift my pencil in order to move the 2 units down to where it restarts. Right? And a gap such as this one is known as a jump. Okay? So again, if I have like a hole, if I have a jump, then this means that the function is discontinuous. This is known as a jump discontinuity. And so the function is discontinuous. A final type of discontinuity is one of the more common ones, especially with rational functions. And These discontinuities are known as asymptotes, right? So whenever we have asymptotes, we know that the function is going to get really, really close to them, but never touch these imaginary lines, right? And so those are, of course, discontinuities as well. If I were to, again, try and trace this function, I could start with the curve on the left, but then I'd have to lift my pencil to draw the curve in the middle, and I'd have to lift my pencil once again to draw the curve on the right. Okay, so I do have to lift my pencil. I actually have to lift it twice. And so that means that the function is not continuous. So again, if I have asymptotes, then this means that the function is discontinuous. Okay? So let's summarize what we just saw. Discontinuities can occur when we have what? When we have holes, right? That's the first type of discontinuity. Or jumps, or asymptotes. Okay. However, not all functions have discontinuities. Not all functions are discontinuous. Some functions are continuous everywhere, and it is actually important that we know which functions are continuous everywhere so that we know which functions are going to behave nicely when we try and take their limits. Even though continuity is not directly related to limits, to being able to find the limit, it does help if functions are continuous. Okay, so polynomial functions are continuous everywhere. Okay, and why is that? Because again, they are all curves. We either go from a parabola to a cubic shape to a quadratic shape, but they are all continuous. So anything of the form x squared or x cubed or x to the power of 4, really anything of the shape x to the power of n, or any transformation of these, right? Or any transformation of the above. So of course I could stretch it, I could shift it, I could shrink it, right? Any sort of transformation or combination of transformations is still not going to affect the continuity of this function. Okay, so really any transformation of the above is also going to result in a continuous function. The second type of function that is continuous everywhere is exponential functions, right? So anything like 2 to the power of x or 3 to the power of x, e to the power of x, right? Anything of the shape a to the power of x, or even logarithmic functions as well, right? Log 2 of x, log 3 of x, anything ln of x, log a of x, all of these, including any transformation of these, is going to be continuous. And again, why is this? Let's recall what an exponential function looks like, right? We are going to have a function that looks like this, or a function that looks like this. All right. And so, of course, they're going to be continuous. Even though we do have that horizontal asymptote, that does not affect the domain. okay? And so we do still say that they are continuous, all right? Asymptotes that affect the range are not counted towards continuity. A third type of function that is continuous everywhere is the absolute value function. So again, the absolute value of x or any transformation. So again, that could be, for example, the absolute value of 2x, or even the absolute value of 1/2 of x minus 1 plus 3, where we can compress it, we can stretch it, we can translate it vertically, we can translate it horizontally, it does not matter. And again, why is that? Well, because what does the absolute value function look like? Just like a big V, so to speak, right? And we never have to lift our pencil in order to draw it. And then finally, the last type of function that is also continuous everywhere is trigonometric functions, right? In particular, sine of x and cos of x. Tan of x, no. Cosine and the secant also, and the cotangent also no. But sine and cosine, yes. And again, any transformation of these as well. These are always continuous, okay? So when discussing is the function continuous, we can either show that there are no discontinuities or find a single discontinuity, because as long as there is one discontinuity, the function is going to be discontinuous, okay? All it takes is one hole for us to say that a function is discontinuous. So generally, we only need to look for discontinuities when we have these kinds of functions. Rational functions, because with rational functions, we can either have holes or asymptotes, or if we have piecewise functions. Because we might have jumps, okay? So these are the two types of functions that we need to be on the lookout for: rational functions and piecewise functions. So let's take a look here. So is this function continuous? Okay, so this is a piecewise function, right? And we have that the function is equal to x plus 4 for any values of x less than 2. And then it becomes equal to x squared minus 2 for any values of x greater than or equal to 2. And so the first question here is, where are you going to check for discontinuity? So what is the problem here, right? Up until x is less than 2, we have a line, right? X plus 4 represents the equation of a line. And lines are, of course, continuous everywhere. So that is not an issue there. And then for x greater than 2, we are also going to have a parabola. We have a polynomial, x squared minus 2, and that is also continuous everywhere. So the problem, of course, is going to be at x is equal to 2, because we want to know, do those two functions connect? Is it that we have something that looks like this? Or do we have a function that looks like this? Because if the two functions connect at x is equal to 2, right, then we do not have an issue. The function is continuous. However, if we have a jump then of course we do have an issue and we have a discontinuity, and so the function is discontinuous. So we need to check when x is equal to 2. Okay, and why? Well, because this is where the definition of the function changes. Right? This is where the definition of the function changes. We go from one function to another, and so it could mean that we have a hole. So let's check. We are going to let x be equal to 2, okay? So then f of 2 is going to be equal to 2 plus 4 for x is less than 2, which is going to be equal to 6, right? And then for x greater than or equal to 2, we are going to have 2 squared minus 2. This is going to be equal to 4 minus 2, which is equal to 2. And here, of course, 6 is not equal to 2. And so that does mean that we do have a jump, right? So right over here, this function is going to have a y value of 6, whereas the parabola is going to only start at 2. So we are going to have a jump, and the function is discontinuous. Okay, so let's write that down. Since 6 is not equal to 2, this indicates there is a jump, and so the function is not continuous. Okay, let's take a look at another example. Is this function continuous now? All right, so we have a rational function, x squared minus x minus 2 over x minus 2. What is our first step here? Well, with rational functions, the first step is always to try and factor them, okay? So if we factor the numerator, we are going to have that x squared minus x minus 2 factors into x plus 1 times x minus 2, which is, of course, going to cancel out with the x minus 2 in the denominator. But the thing with rational functions is that when we cancel out a term in the numerator with a term in the denominator, that doesn't mean that we are going to be left with a line, okay? That's represented by the other term. We actually end up with a hole where the zero of that term would be. So here we're going to have a hole at x is equal to 2, okay? And so since we have a hole, and again, how do we know we have a hole? Because we are canceling out those terms. So since we have a hole, we have that no, this function is not continuous. And again, why? Because it has a hole at x is equal to 2. Okay. Just as simple as that. Let's take a look at a different example. Now, is this function continuous? The function is f of x given by x cubed minus x. So really, what do we have here? X cubed is a polynomial, x is a polynomial. So here I'm going to have polynomial minus a polynomial, which is still a polynomial, right? I am not dividing anything. I'm not factoring anything. I'm just going to end up with a polynomial itself. And we just saw that polynomials are continuous everywhere, right? It was one of the functions, one of the types of functions that's continuous everywhere. And so, yes, it is. Because this function is a polynomial. And we know that polynomials are continuous everywhere. Now for a final example, something fun that we can do with piecewise functions is to figure out what value for the two portions, for the two components of the function, what value makes them continuous. And so in this case, we have the piecewise function given by x squared minus c squared for x less than 4, and cx plus 20 for x greater than or equal to 4. And so what we want to do is that we want to figure out what value of c is going to make this function continuous. So again, we want to figure out what value of c is going to make it so that our piecewise function looks something like this. In this case, we are going to have the parabola first and then the line. And so this is what we want to happen. We want the parabola to meet exactly where the line starts. Okay, so let's just say this is of course not going to be accurate, but this is what the function is going to look like. Okay, and of course that's going to happen where x is equal to 4. All right. And so let's take a look at the situation here. We want to figure out what the value of c is, and of course we know that the critical point, the point that we want to take a look at, is at 4, right? Because that's where the function changes. And so let's let x be equal to 4 and let's plug in 4. So at 4, we are going to have, for the first function, right, f of 4, is going to be equal to 4 squared minus c squared. And this is going to be equal to 16 minus c squared. And then for the second function, we are going to have c times 4 plus 20, which I'm just going to rewrite as 4c plus 20. And now, in order for the function to be continuous, then these two values need to be the same, right? When x is equal to 4. So let's write that down. In order for f of x to be continuous, x squared minus c squared needs to be equal to cx plus 20 at x is equal to 4. And so that means that we need to have 16 minus c squared equals to 4c plus 20. Okay. And so if that is the case, we are going to have here negative c squared minus 4c is going to be equal to 20 minus 16. And this, of course, is just going to be equal to c squared plus 4c minus 4, or plus 4, which is, or plus 4, sorry, pardon me, which is going to be equal to, we can factor it out, c plus 2 squared is equal to 0, and this is going to give us the value of c is equal to -2. Okay, so let's plug it in. F of x then needs to be equal to x squared minus -2 squared. And -2x plus 20. Here, of course, this is going to be equal to x squared minus 4. Okay, so putting this all together then, f of x needs to be equal to x squared minus 4 for x less than 4, and it needs to be equal to -2x plus 20 for x greater than or equal to 4. And I would encourage you to graph this. Desmos.com is a great online graphing software so that you can verify that, yes, in fact, the function is going to be continuous. Okay? And that is it for today. I hope that you have found this video to be helpful. If you did, please give it a like and please consider subscribing and turning on notifications so that you do not miss out on any future uploads. And if you have any questions, then please leave them in the comments below. See you in the next one. Bye!